We can start. Consider a user moving with a constant velocity in an open area. Assume that both the transmitter and the user are approximately at the same heights. The maximum Doppler shift is observed when the user moves in which direction? So when can we expect maximum Doppler shift in such a scenario?
Either moving away or towards line of sight.
Both.
Yes,
Both.
right. So as we all know, the component, theta component that will be involved is cos theta. So it becomes maximum only when it is 0 or 180 degree, when that is when it is directly moving away from the base station along the line of sight path or towards the base station along the line of sight path. Okay. Which of the following curves shows a curve that considers only path loss? A, B or C?
A.
Right. I am just waiting for a few more seconds for others to get an idea.
I think the rest of it is noise.
Yeah, right. So one will be shadow loss, the other small scale fading and all those. So for now, yeah, the answer is A. That considers only path loss is A. So path loss is basically the attenuation that is encountered along the path from the transmitter to the receiver. So it's directly based on the distance. It is considered as one of the phenomenon of large scale fading. So directly, the power of the received signal is inversely proportional to square of the distance between the transmitter and the receiver. So A is the answer that considers only path loss. Okay, in the same figure, which of the curve that considers path loss and shadowing but not small scale fading?
It's B.
Okay. Actually, there's some noise, right? Can you figure out why so noisy? Yeah, I think it's okay now. Yes. We'll wait for a few more seconds. So, as he said, the answer is B. So, this red curve considers only path loss and shadowing. Generally, path loss and shadowing is known comes under large scale fading, and there's something called small scale fading also. So, in large scale fading, you have large fluctuations that is basically over distance. But in small scale fading, we could see rapid fluctuations over a very small distance or very small time period. So in small scale fading, you have again two categories: multipath delay spread and Doppler spread. We'll see about these things in the uh, further questions. So generally, path loss and shadowing constitute large scale fading, which is something like this B curve. So path loss, we know it's direct. It is a propagation loss directly that depends upon distance. Shadowing loss is again a deviation of the received power from the actual value. Generally, it is a result of the obstacles in the path between the transmitter and the receiver. It also depends upon the radio frequency of the EM waves. Is it okay?
Yes, ma'am.
Consider a user traveling on a circular road at 20 miles per hour and let the base station serving this user be approximately at the center of the road. So, what kind of Doppler shift will the user be experiencing?
No Doppler shift because cos theta will be 0.
Cos theta will be 90.
0. Yeah, theta will be 90.
Yeah.
So
Cos theta will be 0, right, yes. So we'll wait for a few more seconds for others to get a feel of the question. So as we discussed, answer is no Doppler shift. We are having the base station in the center and the user is moving in a circular room. Say if this is the user and this is the direction of velocity, the angle made by the direction of velocity of the user to the base station will be 90 degrees. So cos theta will be 0. So the answer is no Doppler shift. You've been introduced to Rayleigh fading in the lectures of week 4. So what are the certain assumptions under which it is valid? Like which of the following is true for when you consider Rayleigh fading?
Delta.
Okay.
it's all of the above.
Right. So generally, Rayleigh fading Rayleigh fading considers a rich scattering environment. That is, you have large number of paths, scattered paths, and there should not be any line of sight component. If there is a line of sight component, then it becomes Rayleigh fading, and the angle of arrival of every component will be uniformly distributed between 0 to 2 pi. As shown in the figure here, if the line of sight path, if the blue path comes, then it becomes a Gaussian channel. Otherwise, the channel is a Rayleigh channel. Is anybody having any doubts in this?
No, ma'am.
Okay. In this week, the questions are mostly conceptual based questions. Very few are like something for you to solve. So, the next question. Consider a system whose input-output relation are given below. Which of them represents a linear time variant system?
A.
Think a bit, like think about the properties of linear systems and time variant systems as well. Try to see which will satisfy everybody. It should be a time variant system.
It's C.
Okay, we'll wait for a few more minutes.
C, ma'am.
Right, okay. So the answer is C.
Why?
Yes.
Can you explain?
Sure. So, when do you say a system is a linear system? When it satisfies the condition that alpha x1 of t, if you give alpha x1 of t plus beta x2 of t as input to the system, then you should be getting alpha into y1 of t plus beta into y2 of t. If you take this signal y of t here, sync of t into x of t, alpha into sync of t into x1 of t plus beta into sync of t into x2 of t, if you take, it will again be the same. We can write it as alpha into y1 of t plus beta into y2 of t. It's shown here. So it follows the properties of a linear system. When do you say a system is time variant? Or first let's discuss the condition for time invariant systems. When you have an input that is time delayed and given to the system, whatever output it fetches should be the same as the output directly delayed by that amount of time. For example, if I have a system here, if x of t is the output, input, and y of t is our output, if I'm going to delay the input by t naught, and if I give it to the system, whatever output I'm going to get here should be same as this output delayed by the same amount, y of t minus t naught. If this question mark, if this output is y of t minus t naught, then the system is a time invariant system. Now let us consider our example, y of t is equal to sinc of t into x of t. If I delay the input x of t, if I give the input as x of t minus t naught, I'll only be getting x of t minus t naught into sinc of t. I will not be getting y of t minus t naught. So this system is a time variant system. Is it clear, sir? Was I audible?
Yes, yes.
Yeah, okay. Okay, let's move to the next question. X and Y are independent and identically distributed Gaussian random variables with mean 0 and variance sigma square. What is the joint PDF of X and Y? X and Y are independent and identically distributed. So what will be the joint PDF?
It's
A.
C. It's C.
Yes. So here, the joint PDF is going to be the product of the individual PDFs, since X and Y are IRD. So 1 by square root of 2 pi sigma square into e power minus x square by 2 sigma square into again 1 by root of 2 pi sigma square e power minus y square by 2 sigma square. So you get C. Okay. Moving on to the next question. Consider a scenario where a reflecting wall and the receiver are on opposite sides of the transmitter. So when you send a transmitting signal, the receiver receives the transmitted signal plus the signal that's reflected from the reflecting wall. The receiver moves away from the transmitter with a constant velocity of v meters per second. What is the equation of the received signal? Can you try to work it out? Can you find what will be the received signal at the receiver? So from here there will be one signal like this. There would be another signal like this. This will be, say, x1. This is going to be x2. So at the receiver, you're going to get sum of x1 of t and x2 of t. Okay, we will see the answer. So at the receiver, whatever we'll be getting will be sum of the direct signal and the reflected signal from the reflecting wall. So let's see how we got the direct signal. So we have the transmitter and the receiver is moving away with a velocity of v, and this distance is r naught. So the direct signal should travel r naught plus v into t before reaching the receiver, as the receiver is moving with a velocity v. So the attenuation will be alpha divided by the distance traveled, which is r naught plus vt into cos of 2 pi fc into 1 minus v by c into t, since the receiver is moving with velocity v by c into t minus what is our tau, that is what do I say, the direct delay component, it's just R naught by C. Same way, if we see the reflected wave, this distance before it hits the wall is d. So it's going to be 2d plus R naught plus Vt. And since the signal has been reflected from the receiver, there's going to be a phase change for this signal. So you will have minus alpha, which denotes the attenuation, alpha divided by 2d plus R naught plus Vt into cos of 2 pi fc into same 1 minus b by c into t, minus here the tau which corresponds to the delay will be 2d plus R naught divided by c. So it's a sum of these two signals.
Ma'am, I have a doubt
Yes.
in this one.
Yes.
So, let's say the transmitted wave will not reach the receiver,
Okay.
and only the reflected wave reaches it.
Okay.
So, in that case, since the receiver is moving towards the reflected wave, towards the reflected wave with a velocity v, doesn't the Doppler frequency increase?
Actually,
compared to the
in this scenario, the reflector is moving away from the wall.
receiver moves away from the transmitter?
Yeah. So if you
No,
see,
the receiver is moving.
yeah,
Is only the receiver is moving.
right. So the receiver is moving, and yeah,
Yeah, is that the reason, sir? 1 minus V by C is moving away.
see, the receiver is not moving towards the reflector wall. No?
No, it's moving away from the transmitter.
Right.
Since we are assuming both of them are in the.
Actually,
Okay, fine.
Yeah.
I thought the reflecting wall is on the other side. Oh, then it's correct.
Yeah.
Thank you.
Yeah. Okay. So the next question. Okay. The next question is also dependent on the previous thing. So what is the difference between the maximum and minimum Doppler shifts? So I'll keep the equations here. So what is the Doppler spread? Basically, the difference between the maximum and minimum Doppler shifts. So what is the Doppler spread at the received signal?
Two times FC V by C.
Okay, you have
Should be
to
zero.
you have to find the difference between the maximum and minimum Doppler shifts.
It will be zero, right?
Yeah. So the answer would be 0. You see here, for this it's again V into Fc by C, same way V into Fc by C. So the difference is 0. So the Doppler spread as in is 0. Is it okay?
Can you show the next question? So this should consider the same scenario, but
Yeah.
among all the multipath components.
Yes.
Okay.
Same way, the next signal is also in a similar thing. So let's read the question and maybe go to those equations back. The superposition of the given two multipath components result in constructive interference when? That is, basically you have to find the phase difference between the two components and see when we could expect a constructive interference. Is the question clear? I'm going on to the equation. So when can constructive interference occur?
when the phase is a multiples of K, okay, K pi.
when 2D divided by C will be an odd multiple of pi.
Okay. Just few more seconds. I'm just waiting for others to make a try. Okay. So let's see the answer. If we see the phase difference between the two components, first component is 2 by fc into 1 minus b by c into t minus r naught by c. For the other component, it is yes, so it's actually 2 pi fc into 1 minus b by c into t minus 2d plus r naught by c. And since there was a negative sign, that is, we are expecting a phase shift of 180 degrees, it's plus pi here. So I'm trying to find the phase difference between the two signals. What we are expecting is the phase difference should be equal to 2n pi for constructive interference. So it is 4d fc by c, that should belong to 2z plus 1, that is set of odd integers. So 4d fc by c should belong to set of odd integers.
Madam, why plus pi is added while calculating the phase difference delta theta?
Yeah, so for the reflected signal, we are expecting a phase shift of 180 degrees.
Okay. Yeah.
Yeah, that's it.
Okay.
So we'll move on to the next question. What is the delay spread in this scenario? I'll go to the equation. So what is the delay spread in this scenario? What's the answer? What's the delay spread? What's the difference between the max and minimum delay of the path?
It's 2D by C.
Right.
Just difference.
Yeah. So the answer is 2d by c. So the delay spread is 2d by c. What is the minimum time required for magnitude change or phase change in a channel?
Coherence time?
Yes.
Delay time?
It's actually coherence time. So coherence time is the time duration over which the channel impulse response is considered to be not varying. That is, in this time, we could expect a correlated impulse response. So, it is a minimum time required for a magnitude or phase change of the channel to become uncorrelated from the previous value. So generally coherence time, you say it's a time duration for which the channel impulse response is considered to be not varying.
Yes.
Okay. What is the relation between coherence time and Doppler spread? How do we relate both?
Inversely proportional. A.
Yes. So the coherence time is always inversely proportional to the Doppler spread. When channel's coherence bandwidth is greater than the transmitted signal's bandwidth, what kind of fading occurs? When the channel,
Frequency non-selective.
yes. So when,
Frequency C.
yes, frequency non-selective, or you can also call it as flat fading. Flat fading means the channel's coherence bandwidth is greater than the transmitted signal bandwidth. That is, the channel is almost like it is equally affect the like the channel's attenuation, or the how much it will affect will be almost equal in all the frequencies. So based on multipath time delay spread, small scale fading can be of two kinds. One is flat fading, the other is frequency selective fading. In flat fading, the bandwidth of the signal will be way lesser than the coherence bandwidth of the channel. Which we can also mean like the delay spread will be lesser than the symbol period of the signal. Now, in frequency selective fading, bandwidth of the signal will be greater than the bandwidth of the channel. And the delay spread will be greater than the symbol period. Is this okay?
Yes, ma'am.
What is the relation between coherence bandwidth and delay spread?
This is also inversely proportional.
Yeah. So when you say that you have a larger delay spread, it means that your coherence bandwidth is very small. Coherence bandwidth and delay spread are inversely proportional. Right. What is the measure of the maximum frequency difference for which signals are strongly correlated in amplitude? To what term do we refer this to? That is, it's the measure of the maximum frequency difference for which signals are strongly correlated.
It's a narrow bandwidth signal. Or within
Okay.
the coherence.
Yes, you're right. Just, I'm waiting for others to understand the question. As I said, the answer is coherence bandwidth. Generally, coherence bandwidth is the measure of the frequency range over which the channel is considered to be flat. That is, the signals with the frequencies in the range of coherence bandwidth will most likely experience correlated amplitude fading.
Okay.
If a set of subcarriers in an OFDM system are in fade, which seems to be the best option?
A. Do not transmit it on the subcarriers.
Yes, I think that's the best option. Because in the case of OFDM, like our whatever signal, whatever we want to transmit, we are placing them in subcarriers. If some are at fade, then it's better not to transmit data in those subcarriers.
Okay, ma'am.
Okay. When the channel's coherence time is less than the time duration of the transmission signal, what kind of fading occurs? Like the coherence time is lesser than the time duration of the transmission symbol.
Fast fading.
Okay.
Time select.
Okay. As he said, the answer is fast fading. Based on Doppler spread, small scale fading is of can be into two categories. One is fast fading, the other is slow fading. In fast fading, the main criteria is the coherence time, channel's coherence time is lesser than the symbol period. So we are expecting channel to vary within the symbol period itself. So it is fast fading. The channel variations are faster than the baseband signal variation. In slow fading, the coherence time of the channel is greater than the symbol period. So we are expecting the channel to almost remain constant for the particular symbol. So channel variations are slower than the baseband signal variation. So the answer here is fast fading.
Okay, ma'am.
Yeah. Okay. Can I move on to the next question?
Yes, ma'am.
Large scale fading refers to attenuation in dash.
Signal power.
Yes. So large scale fading means it will refer to the attenuation in signal power, or it's directly the path loss due to motion due to the distance travel. Now, when there's attenuation in amplitude or phase, what do we refer to as? That will be small scale fading. So small scale fading will refer to the attenuation in amplitude and phase. Fading is caused by interference. True or false?
Is
False.
false.
Okay.
Fading is to distance Doppler.
Generally, when does fading occur? Even if we consider a wireless communication scenario, when we are transmitting from a transmitter, the signal gets scattered, and at the receiver,
It adds up.
yeah,
So
right.
it's kind of like interference.
Yes. So fading is basically the constructive or destructive interference of the multiple signals from the scatterers or the signals from multipath. So basically it is caused by interference between two or more versions of the transmitted signal that arrive at the receiver slightly different times. Basically multipath. Is it okay?